Okay, everybody. Okay, everybody. Okay, thanks. It's my pleasure today to introduce our student, Roy Smith. Many of you know him, those who don't. Roy's originally from New Zealand, where he got his bachelor's degree and worked for several years before he moved to Caltech Tech, where he got his PhD in 1990. Roy's worked on a whole bunch of interesting problems in system identification, robust control, and lots of consulting and application problems, JPL, among other places. He was on faculty at Santa Barbara for 20 years, and then he moved to ETH in Zurich, which has a mandatory retirement age. Therefore, he is now Professor Emeritus. However, he assures me he's not retired from doing research. He's only retired from getting paid to do research. So with that, I'll let you talk. Go ahead.
Thanks very much, Jim, and thank you. And so thank you also for the invitation. It's great to come and to see a lot of familiar faces, catch up with the nice weather this part of the country at the moment. So as advertised, I'm going to talk to you about data-driven control. I'll deliver, I think, what's kind of a mixed message in there, but we'll get into that as we go. And then we'll see what we can say and how it relates to some of the things we already know and where it's potentially useful. So without further ado, oh, by the way, feel free to, if you have a question, put up your hand and I'm happy to answer on the spot. I won't monitor the chat. It's too distracting. So if you have a question online, we'll try and get them at the end. Okay, so sort of a pipeline for design and implementation of a control system. Here's a very rough sort of pipeline, but a classical approach. The definition of classical is a function of time. It usually means before the current PhD students, but this is how we used to do a lot of stuff. We would have typically some physical intuition, physical models of a system we wanted to control. We would probably have some experimental data which would corroborate those models or add to them. And we'd go through a big modeling step to get a good model of the system. From that, we would design a controller and then it would implement it. Of course, it never quite works as you expect. So then you'd probably go back and repeat this control design. And if you realize you didn't do enough, you'd probably go back and repeat even the modeling step in times. But that was a sort of classical one. Now, what's currently sort of on the horizon is this idea of data-driven approach. And here the idea is to skip essentially the physics and the modeling and just go from signal data straight to control design and from then on straight into implementation. Of course, you would expect that you might have to go backwards and forwards as you learn more about the system, but it's essentially trying to remove some of the physics and modeling, or at least simplify them in this sense. So I'm going to focus on this. It's called a data-driven approach, but that's a very general word because the last 100 years of control has been based fundamentally on data anyway. So you could describe a whole lot of system identification model as data-driven, from the time of Gauss, basically, we could doing data-driven identification. So here we can look at sort of the motivations. So I'd express this as a push and a pull. So the push is that, we have potential difficulty with some of these things. We'd like to try and avoid them. And this is trying to decide what structure our model should have, what sort of model we want. We might decide what sort of order. There are a lot of parameters that can go into structural choices for our models. We would select an identification method or methods. There are multiple choices. Some might be better than others on here. And, how to really include the physics in the model could be quite difficult. Some physics is easy to include in PDEs, for example. It's rather difficult to get into models we can handle in a control context. And the pull on the other side, what's attracting us towards it is increasing availability of data. That's sold as a motivation, and it's true that there is certainly a lot more data available, but it's somewhat limited. I mean, in many domains, there's a lot more data available, but when we're talking about dynamical system, data comes to us one time step at a time. It doesn't get any faster than that. The parallelization of data for many machine learning methods, for example, parallelization gives you more data. If you're doing recommendation systems, then the more people you have feeding in gives you a lot more data very quickly. For us, the data is not quick, typically, and so we are concerned about having good data and dynamic data in there. We might be able to bypass modeling considerations. That might be partially true. People say data determines the model, but I'd say be prepared to be lied to a little bit in some of that. It doesn't always determine the model you want. It'll give you a model for something. And then we have the potential to adapt the data or the design for new data by continuing to collect data. One thing that's a little bit dangerous here is it raises an issue of the informativity of the data that comes under control. And a reason which I think is a nice one, we have a potential to automate or semi-automate the design process. I'm not saying that we hand it off completely, but it could make the design process easier. So that's where we sit. I'm going to give you a bunch of applications here. Now, you usually see a talk where people give this application and say, my work is applicable to this and this and this. And actually, what I'm going to do is a little bit the opposite. My work is not applicable to any of the things that are on here. And I'll point out why that is. It's applicable as a warning not to try and do this in these situations. So these situations are either, so look, in the first one, safety critical situations, extremely expensive. This is a high purity distillation system in an oil refinery. Either repetitive with mass production, both of the robots and of the cars. Here we have an opportunity. This is landing a spacecraft on Mars, and when we were working on that, there had been precisely 3 measurements of the density of the atmosphere taken at that point. There's just not enough data to work with. And here we have a distributed control system for a optical interferometer in space. And here we have actually, this is an automotive system in there. And this is what's the guy's name? So Horatio Nelson Jackson, also, he did the first crossing of the continental United States by automobile in 1903. So in this case, maybe the only control system is him himself in this, almost the only one. But nowadays, of course, there's many, many loops in vehicles. Now, why might you not want to be using data-based control in these places is that the concept of state and that has meaning far beyond its use and control. So it's in many systems, it's in a hierarchy where the upper levels for coordination, scheduling, planning, communication over multi-agents, they rely on the knowing of the state of the level down below, and that state has valuable information in there. And it has a physical interpretation which you have to know to do it properly. It might be safety critical where you want to exercise your model of the system, your control systems in domains which you would not want to fly your plane in this. You want to find out when do the wings get ripped off in there. And so that's not something you want to determine experimentally. So it's a very high value in this, so that the resources available for modeling pay off in getting a very good, very accurate model in there. These mass production causes payoff in the model, that you spend your time, you get one good model. If you're going to make many, many versions of this, that pays off through the mass production aspect. So all of these situations, this one, it's a hierarchy, distributed hierarchy here. And so you've got to be careful when you're flying these satellites, they're reflecting light beams to this one, that no satellite moves across such that its thrusters lay ions on the optical surfaces of another one. You've got to know where they all are. For the communication, you have to know where they all are, and you have to position them to, in this case, for the satellites, within centimeters over 10-kilometer ranges. And the communication hierarchy, there's no multipath here, and so occlusion kills communication between satellites. If one gets in the way of the other one, they can't communicate. So all of these hierarchy decisions about how to reorient the system and that depend critically on the state of that. And so you really have to know the actual state. So I'd say those are the situations where what you know about system identification, go for it and do a good job, and it pays off. So data-driven ones, where might it pay off? So the cases where you might get some real benefit are low-value cases and heterogeneous system where the value comes from the aggregated case. So the classic example I have here is control of thermal energy in buildings in this. You know, this building is under control. I don't know how much they spent modeling this system, but I have done this quite a bit. And essentially the payoff is really not worth spending a huge amount of time on the model. You want to be able to do it quickly and efficiently, but buildings consume 40% of the energy, certainly in Europe. US is similar, and they generate about 40% of the CO2, both in Europe and the US. So any saving you get in aggregate over all of them is definitely worth having in that. But for the individuals, it's not worth putting that investment in. So that's a case where you really want a simple, almost semi-automated, easy way of getting a controller which gives you some benefit. Another one is where you have limited knowledge or privacy, say multiple agents, not necessarily in a dynamic or coupled environment where they don't necessarily want to share everything. So the only available information to you might be through those signals in that for commercial reasons or other reasons. So you have limited knowledge and you're really restricted in what you can do. Or the modeling domain might be incompatible. This one I'm not really sure of. I'm kind of thinking about this one still, but where you've created a very nice digital twin, it's easy to simulate, but it's extremely hard to embed in a control design because it's just far too complicated. It may be solving partial differential equations in doing so. So you may be able to use the simulation abilities to really exercise the system and get a simpler model for that. That one, I say, try it out, see if it works. But that's a possibility. One example there might be modeling aeroelastic effects for wing loading or models, which can be very high order models, but to get a nice controller, you may want a much simpler model. Okay, so the potential here for these, as mentioned, is energy systems, building control systems. So this is on this side is a building. We had control of this building for 2 years. And so together with the project with Siemens, we alternated 3 months with MPC and they had 3 months with rule-based controller. Then we analyzed the comparative results and we went backwards and forwards and we improved both. And actually we kind of converged the two methods a little bit in there. We don't have many actuators, about 5 or 6 I've got listed there. And we're trying to control the room temperatures. We built a first principles models. They had 1,500 states. Hankel reduction, we got that down to 15 states with 0.1% error, fine. And so we have proceeded, but it took a PhD student about 2 years to get a nice model, but we really wanted a very nice model for that. And we've, as I said, ran it over these 2 years, and we saved in the energy use of this building about 15%, which is, given how it wasn't built to be controlled well, this is pretty good. And that came to $5,000. So you think, okay, we have 2 years of effort, and we're getting a payback at a rate of $5,000 a year. How long is it going to pay for the person to go and do the system identification and model control design? Yeah, no one's even going to do it in there. But 15% saving across a country or a continent makes a huge difference. But none of us like to live in a building that's exactly like someone else's building. You get an architect to build a building, it will not look like any other one, and this is for sure. So the models are all going to be different. So that speaks to a domain where really simple, efficient methods that get you something to pay off. These are energy hub systems. This is a building built in Switzerland, which essentially where architects plug in and out modules to do different design tests, and the modules get shuffled around every 2 years in there. And they also they model energy systems as well as architectural systems. And there's a sort of, you have a hub which has many sources of energy, electrical grid, gas grid. It might have biomass, so it burns fuel, chiller, battery. So it has essentially sources of energy, conversion methods, and storage methods in multiple domains. And then it optimally balances between a connection of customers in there. And again, you may have privacy concerns that the customers don't exactly want to tell you their production schedules and the energy use. And so you have to figure out what's needed by only looking at the signals. So this may be also a potential application where these are useful. Okay, so model predictive control is kind of the basic control structure I'll talk about. And I assume it's fairly familiar to most of you. At least the faces I recognize have seen this before. So what you're doing is effectively you have a rolling horizon, and over that horizon you predict what you should do as a control for your system. So you predict, for the buildings, we would predict 54 hours in advance. We'd plan out our control steps for 54 hours. And so that was enough to look over the weekend to when the people would be back in the building. And then every 15 minutes, we'd measure the rooms again and we would replan. And then we kept rolling that horizon along. And so that was the structure. So we typically have a cost function, here summed over some horizon. I've got TF there, just means forward time. And so that's what we're trying to minimize. Now, cost there would be energy cost. It might be a CO2 penalty. There are a variety of things you could put in costs. And you were optimizing over the inputs and outputs of your system, the room temperatures and all our control actuation. And then I've just said, this is subject to that U and Y satisfy the dynamic model. So that could be a state space representation in there. It could be a variety of other things. And you might have some operational constraints. U lies within limits, of course. So I'll call that capital U. And you might like the output, the temperatures to lie within limits as well. But the real question we're addressing, I guess, today is what should we use as the model here in that? And so I'm going to look at data-driven methods, or what classically these days we think of as data-driven. But let's talk a little bit about the philosophy. I promised this quote to someone. So applicability of the model. So George Box said all models are wrong, but some are useful in this. And so we want useful models for sure. We also hopefully would like to exploit the principle of parsimony, in other words, make as cheap or as simple as possible in this context. So you make it as simple as possible, which you've heard of as Occam's razor, so you remove extraneous assumptions from the model. And that makes it easier to check your assumptions. Are we assuming only what we need to, because simpler models are more easily falsified. You can look at some data and say, no, that doesn't agree with the model. I need to fix the model. And you also require fewer parameters. Fewer parameters require fewer data for identification in that. And that can be kind of important about how much is needed. This is my only source of a picture of William of Ockham for Occam's razor. But anyway, it's probably not very accurate. All right. So these are the typical models we see, and we're all very familiar with them. Pulse response model, potentially infinite number of parameters in that one for an exponential decay, but we often truncate it. Real rational transfer functions are in here, and state space representations. So I'd say these are pretty common. This occurs occasionally, but all of these can be put into robust control, but also model predictive control interpretations. So those are the systems we deal with. And what I want to do here is just introduce you, I'm sure most of you know, but that what people call data-driven models or Hankel models or behavioral models, or I call them system matrix models. And I should emphasize here that they are actually models. People say we don't have a model, but you do have a model. You just have the different representation in that, but it's still a model because you're using it to predict what's going to happen. That makes it a model, no matter how different it is from these particular cases. Okay, so here's the framework derived from Willems' lemma. So supposing we've got some sequence of input-output data points here, and I'll call them U and Y. U is the input, Y is the output. And let's say I've got capital K of them. I simply stack them up. So U1, U2, et cetera, up to some horizon T that I'm interested in making a prediction over. And then I just shift by one time point, U2, U3, T plus 1, and I stack all of my data into these columns for the input and for the output. And if I've got lots of data, I just end up with lots of columns. But this dimension, the row dimension, is the horizon I'd like to do my prediction or my control over. So you stack all of those up. They don't actually have to be Hankel matrices. You can, as long as they are linearly independent. And they span the space of possible trajectories. But those things are easy to check. Hankel is the one everyone uses, and it's a fairly efficient one from the point of view of how much data you need in there. Now, Willems' lemma has this nice result, is that a U and a Y is a length T input-output trajectory of the system if and only if you can find a vector G such that the input-output trajectory is equal to these Hankel matrices multiplied by G. So you stack them up. And it represents every possible input-output pair you can have for the system. Now, you can choose any U you want, of course, but you don't get every possible Y. Only the Ys that will be produced by the system. And so this matrix HU, HY that I have here is actually low rank. It's certainly, you want the HU to be full rank in here, but the HY will be low rank, and the rank of that will actually be the state dimension. If it really is a linear time invariant finite state, you'll get the rank of this whole thing, not the Y by itself, but the rank of the whole thing is the rank of HU plus the state dimension. So you can find out what the state dimension is, but it characterizes every input-output relationship. And because this is if and only if, all linear systems can be captured. The linear time invariant input-output systems can be captured by these two matrices like this. So you just need to say, okay, now I have a model, and my model just means take one long sequence of U's, one long sequence of Y's, form these matrices, stack them up like this, and I can work out what every other possible input-output combination is. So that's a model of my system. And it seems like a very powerful thing. You don't have to do particularly much to get it. You just have to take enough data. One thing you do have to be careful with is that it's what's called sufficiently exciting. And in principle here, in this context, what this means is that when you stack your data up like this, and you've got T rows of it down here, it has rank T in this. You've got lots of columns in here, but you at least have rank T in there. Then your data is sufficiently exciting. Now, rank is a very yes-no type condition. In practice, there might be small singular values. You should avoid small singular values. And particularly, you should try and keep the condition number reasonable there. But that's essentially what it means to have good data, because if you've done that, then you've excited all the modes of the output, and you get all the possible outputs in Y, and you're good to go. Okay, so that's a model, and it just talks about U and Y. So how do you turn that into a prediction model? Well, you split U up and say, I'm going to consider part of my U to be the past and part to be the future. So think of yourself in the middle of this, of a particular input UY, and say, okay, everything, this part is the past, I'll call the past, everything here is the future. And you could make these the same length, but, you know, those are your horizons. Now you do the same for Y, you split it up, and now you look at HU and you split it again. I've got P for past and F for future there. And so you split the pieces up for HU, HY, and now you shuffle them slightly. If you just put them, stack them as splitting them up, here's the past U in my matrix, past and future U, I should say. Here's my past and future Y. And that means all U's, all Y's that I can get. So now what you get is you say, okay, supposing when we're doing the control problem, we've just seen some data coming by. And so we say UP, the past input is known. I just watched this input for a while, and now I have this, I'll use this gold thing to say, oh, I know this quantity. And of course I was measuring the output, and so I know it. So I'm looking back at my past collection of data. And so now I know what these two pieces of the vector are, and these two are. So that gives me some information about the G here. But what I want to do for control is I want to choose a future input to get a particular future output. I want to get the optimal output here, and I want to choose that. So what I'm going to say, if I specify U, I want to figure out what was the corresponding Y going to be. And you can easily see it. A simple solution for this is for G to just basically do the pseudo inverse of the pieces you know. So you specify the past input, what you think as a future input, and your past output. Take the pseudo inverse of this, gives you a G, you just multiply it by the HY, and it gives you the Y. And that gives you an exact prediction of what's going to happen. Perfect, because it models your dynamics. The matching of the UP-YP essentially sets the initial conditions to where you are now. So, and then when you set UF, it'll tell you what you get for YF. And you can easily do that, and it works extremely well. So you can write down your control algorithm in this form. Now, this was called Deep C because of my punning colleagues. And so you could have a typical cost function, say a quadratic cost on the output tracking. You're tracking a reference R, quadratic cost on the input. And now you write down your model of the dynamics essentially as just that. It's a linear constraint. So it's a quadratic objective linear constraint, very easy to satisfy this. You might put constraints on UF and UY. And actually, if you don't have constraints on the U, that has to lie within segments, you could actually, it's not just a linear constraint. With that quadratic optimization, you could substitute this in and then solve it analytically in there. So it's a very, very simple problem to do. Now if you did that analytic solution, you effectively get what's called subspace predictive control. And that's, good.
This assumes no disturbances.
Yeah, we'll get to that. It does. And that's a really unfortunate thing to miss. So yes, so this is subspace predictive control. And that was published in 1999. It's been around by the people who basically did a lot of the development for subspace identification in there. It has a variety of other variants which do different things. But one thing to notice here is that the G has two functions as you write it here. It's matching the past input-output data to give you initial conditions. And it's also choosing what's the best future YUF to minimize the cost function. And those are somewhat in conflict in there. If you just write them there. So the typical approach is to regularize the G in this. And so there are a variety of ways of regularizing G, but the regularization and the optimization is over here. And you can assume that maybe there's some noise on your past measurements and you put in a slack variable for that. And you penalize it, so you think this noise is small, and you penalize the size of G as well, because you don't want it to get too large in order to fit the small noise. So that was the more practical version of DeepC in there. And so it's been modified a variety of places, but to trade off here, these regularization parameters, lambda G, lambda Y in this slide, they have to be chosen. So people have to essentially search the parameter space, look for heuristics in this. And actually, in this case, this isn't really necessary. For a linear time invariant system, it's not. You can do something else. But another problem comes up when I come to this, and this motivates why people are doing regularization, is that certainly at least the Y is going to be noisy. You never get noise-free measurements. So you've got noise in here. So now when you look at this constraint, this HU, HY, and so you're trying to find this, I said it was low rank. Now, if there's no noise, that is a low rank matrix in there. But if there's noise, then generically it becomes full rank in this. And so now, because that's a full rank matrix, there's not really constraining G into a certain possible class. So any G can work, so you could just pick the G that minimizes your cost function, ignore the initial conditions. And the reason to avoid doing that, well, one way is to regularize the G to make sure that it doesn't do too much of that. So regularization becomes important when you put in noise, and you really need to get a reasonable solution. There's some work on maximum likelihood estimation of G in order to choose a value, but I'll do something a little more developed than that point when I talk about this in a few minutes. But another thing to consider here is, where did this data come from? Now, and I said not all data is equal. So if you had a high fidelity simulation, a digital twin for your system, and you can control and run the experiments, you can put in whatever inputs you want, you can get very nice noise-free data, but then you have a slight sensitivity to the quality of your digital twin. If it's a really poor one, then obviously you'll get poor results. But you can get good quality data from it. If you run a dedicated experiment of this, where someone gives you the system and lets you play with it for a while, then you could certainly make sure that the U is sufficiently exciting, but you will have some noise. I'll put this as sort of an orange thing. But you can do experiment design to minimize your problems in that. Now, this gets us back into the old field of system identification. Things like input design, experiment design are big parts of that field. And so they're still with us. And we didn't get away from that here. It's still the case. If you use operational data or historical data, then there's a real potential problem here. And that's that certainly it'll be noisy, but it'll also probably have a persistency of excitation problem. So the U's you find, if the data is not doing much, obviously if U is constant over long periods of time, that matrix isn't full rank. If it's totally constant, it's rank 1 in there. And you're looking for at least rank the length of the horizon. So this is a persistency of excitation problem. And if you don't get to control or you don't get to excite the data that you have, then you can run into this problem as well. So one of these first two situations is a more reasonable one to be in there, or a more desirable one to be in, I should say. Okay, but there's another approach to this. And so this is what sort of started me on this a while ago. So in that, actually, there's a natural decoupling between initial conditions and predicting the future input-output. So for linear systems, we always do, you think of an initial condition, and then you think of a zero-state response, and you sum the two together, and you'll get the input-output response of a system of this. And so, but that's all that's going here. The initial condition looks a little different because it's encoded into these future and past Y and U, but you can think of splitting G into two pieces. And these two pieces can be, I'll call them GP and GF. So GP, its purpose is just to fit the past data in that. And GF's purpose is just to control what the future control input should be, sort of optimizing the zero-state response in that. So you can write GF being decoupled in there. I should have said, they're not always orthogonal, but GF can be orthogonal to part of this vector. So this is terrible notation. But basically, you pick GP to give you the best match to the observed past. And then you pick GF to give you the output that's best for you with the required input, and maybe subject to some constraints. Now, the key thing is this choice of GF does not affect UP or YP in there. So it doesn't change your previous estimate. So causality alone just splits it into two pieces. So you choose GP to match the initial conditions, GF to satisfy a control objective. And that gives you a very nice result. And you don't need any regularization at all, even in the presence of noise in this. So that's the approach. I'm going to do it now differently. I sort of explained it in the context of this G matrix, but that's also not the most efficient explanation either. But conceptually, at least, this is what's happening. So you minimize now over all four pieces, GP, GP, GF, UF, YF. So this is the UF, YF is choosing your future input and output, and the GP at least is choosing your past input. So here's your control objective again over the future horizon, subject to choosing a GP to match the initial conditions from the past. And now to generate the future, you need both the GP and your new GF variable, because this matching of trajectories will give you some response in the future, so you account for it from GP. And now this is the degree of freedom you have in your controller. And you exploit that degree of freedom and you minimize that cost function. And it's fairly straightforward. Yeah.
Why not just solve? Why is GP an optimization variable here? Just
I could just pre-solve it. I mean, it's just convenience and to make it look as much like the other one as possible. But yeah, I could. I could keep pre-solving things in here as much as I could. But yeah, that's just to make the analogy a little clearer.
to make it any better though, like in the original papers, why wouldn't they have done? I would have thought that's how you would have framed it to begin with.
Yeah, I would have framed it that way. Yeah, why wasn't it done? I'm not entirely sure. So I mean, I know the people who did it, but I'm not entirely sure why. So, and one of the regularizations comes actually pretty close to doing this by forcing a causality requirement on the part of the GF. So it's just, I guess I've stepped away from the regularization, just looked at this more from a classical point of view. Okay. But actually, there's even some redundancy in this. So remember I said, well, we have this representation here. Let me choose it. So there's the past input, past output. So there's a representation there. And what I'm going to do is take that. And remember, this has rank, which is equal to the number of the horizon on U and the state dimension. So that is a low rank matrix. Think of it as having many more columns. So plenty of columns in there, but the rank is determined by the rows and whether or not they're linearly independent. But you can see that you get nice data, U data, you get full rank H, but you're going through a linear time invariant system of finite rank, and so then you get a low rank Y. But if you do a QR decomposition, you can calculate a lower triangular matrix here and here, representing this equation. And there's a huge null space in there because there's lots and lots of columns, and almost all of them can be thrown away. Once you've got a QR decomposition, or this is a lower triangular decomposition, so you can parameterize the null space, but you only need to keep this representation because it's not an approximation, it's a decomposition. You can reconstruct the entire matrix if you want in there, but keep only that piece. And now when you solve your GP, you're just solving this equation, and I'll change this GP variable to XU, XY, and that's slightly suggestive notation here. So this XU, XY, now you can see that the past U tells you what the UI should be. This is lower triangular, you can invert it. If it's sufficiently exciting, you can invert it. The YP here, this is a matrix, but how many columns this has depends on the state dimension. So it has the same number of columns as the state dimension. So you have a lower dimension XY there and there. If you want, you can reconstruct the GP if you like, but I'm just going to start using this representation of this because it's an equivalent representation to this. All I've done is I've just taken the null space away from the matrix. And so I can do the same with the future matrices that generate the future, but I'll start by first making them orthogonal to the ones that generated the past. So I'm using an orthogonal model there, and then do exactly the same thing. And I will get, again, lower triangular matrices, but in the noise-free case, there's a lot more zeros in it. And all of these zeros over here, this width is just essentially for the YF, these are just the horizon ones, and they're both actually lower triangular for causal systems. So I can pick, if I want to consider a future input, I can pick a vector Z, which matches to that future input, and that uniquely defines the output I'll get. So here's a smaller version of Willem's lemma, and essentially I could say it as, if I take these matrices calculated by doing QR decompositions on the data, every possible input-output pair of the system can be generated by an XU, XYZ vector like that for every linear time invariant system. And again, I just used one data thing. I didn't do any approximation at this stage because it's just a QR decomposition. It's actually an equivalence of that. So it's just a smaller version of this because the number of columns I have now is not the whole data length. It's simply horizon length, state dimension, horizon length. So it's a much smaller decomposition generally, but it can also conveys the if and out, if and only if representation for linear systems. So I'm going to use that as my representation and put that into my models and proceed from there. Okay, so I can do that, and you'll see, let's suppose I've got some noisy data here. And so Y is corrupted by noise, and let's say it's stochastic noise, and I'm just going to use scalar times the identity for the covariance matrix. So I can easily look at my past data here, calculate what XU should be. Then I can estimate XY even from noisy data by just doing the least squares optimal solution. I've just written the normal equation down there. So I solve for that. I could do weighted least squares if my covariance wasn't diagonal. And now once I have that, I've got the XU. I have an estimate of XY. It's estimate because there's actually noise on the measurement there. And I get an estimate of the Z I need by inverting the UF. And then I get Y by just plugging it in this equation. And so I could go through all those steps, but actually, I said, this has some properties when you've got no noise on the data. One, if there's no noise, V equals 0, then you get the exact prediction of the future, zero error, unbiased. It's unbiased, and you can actually analytically calculate its covariance. So your prediction of the future horizon, you have a formula for the covariance of that. And you interestingly notice it involves the inverse of U in here. And that's really just comes from the quality of the data. If you have small u, weak data, you get a big covariance error in your output estimates. So what you'd expect, but the really nice thing is this YF is a linear function of past input, measured output, and the variables you have x, u, x, y, z. So it's linearity on all of these variables. So I could actually just solve that in this if I didn't have any input-output constraints to satisfy. And so if I do that, let's say I'm given the immediate past u, the immediate past y, and I want to minimize this cost function, it's just subject to these three matrices, which you can calculate by just solving the procedure I had. And you get the exact solution. So it's one matrix equation, gives you all possible input-output combinations in this. And it doesn't require any regularization in the presence of noise in that, because you split the estimation and the control design pieces into two orthogonal bits. And that is essentially the equivalent of subspace predictive control, which they got from a completely different point of view. And this, when I say essentially the equivalent, if I put in scalar times the identity for the noise, it's equivalent to, in MATLAB, 10 to the minus 12 in these matrices. And they didn't even use an assumption of causality, but why did it get it to machine precision, basically? That's really kind of interesting. But this is really subspace predictive control. It puts the closed loop solution in there. So there we have a useful predictive controller in that, which implementation-wise could be potentially easier. So now, we're at this point, and so I've simplified the method down, but I haven't done anything more than throw away the null spaces and then parameterize into past and future in a reasonable way, and then just solve the equations. So there's not that much that's really a contribution here, I would think, particularly when there's a paper from 1999, which effectively got the same answer a different way. But now I want to try it out. So the theoretical results I gave you assume that I had no measurement noise, but of course I have measurement noise on there. And there it's harder to make a predictive one. So I'm going to, rather than do theory for that, I'm going to simply try some examples. And you're all going to tell me off for this. I'm going to use an example where you should never use data-driven control anyway, and you'll see why. And I apologize for that. But my motivation for using this example is it's something of a benchmark problem in a lot of the model predictive control literature. And there was a nice paper, very well done paper, written about comparing all the different data-driven methods, and it used this problem of controlling the longitudinal dynamics of a 747 as their kind of test piece, one of their test pieces. You've got two, we're close enough to the aero department that I'm not going to explain it in great detail, but two actuation inputs, which are essentially the throttle, the thrust you have under the wing, the elevator angle, and then you're measuring the velocity, y, so in the body axis of y1, y2 are just input and output. You're actually measuring xb dot and the climb rate in here. And you notice about 747s, the engines are hanging fairly low underneath the center of gravity. So putting a lot of thrust on the engine gives you a torque, significant torque on there. So that's the example. It's only a 4-state system. And here's the model data. So this is basically an excitation where I had a PRBS signal of 250 seconds, exciting both the thrust and it's a very simple model, so it doesn't really have the engine dynamics or anything in there, but it tells me the horizontal velocity I get and the climb rate in these two plots. So you see it goes up and down. There's definitely a dominant frequency in there. And for the aero engineers who recognize that as a phugoid mode, it's present in that. But here's the model data. So I've got essentially 2,500 data points to work with in this. And there's noise on it. So my horizons are only going to be 30 samples and 20 samples. So 3 seconds into the past, 2 seconds into the future for my control, which is really only a very small piece if you look at this picture here. And now I'm going to do a step response, try and get a step response in the velocity without coupling in too much. And I'll do some Monte Carlo runs. And these are the results. And I've compared a variety of things here. So here's the method I just described to you. And there's a step response with the velocity stepping up beautifully. There's a shaded one which is showing me plus or minus 1 standard deviation in this. There's a bit of coupling initially in the climb rate. It's controlled easily. This is what's called generalized data predictive control, another variant, regularized variant. Gamma data driven control, another variant with regularization. And this I just got out MATLAB, ran Info-SID, ran Kalman, put it in a loop, and then design an MPC controller in this. And they're all pretty close to identical in this, which shouldn't be a surprise because it's a linear time invariant system. All of these do really well. So in the classical methods, Info-SID, Kalman filter, they're essentially behaving the same. Just to complete the picture, here are the inputs. You see some slight differences here, the input actuation. Of course, you can't actually change the thrust of an engine, the size of a Boeing engine and that quickly, but you know, it's a simple model. They all do pretty well. And then if I plot the mean square error here, and I'm using box plots, which are showing all the data, or just the integrated absolute error, so you can see a little more carefully the differences between them. These are the regularized data-driven one. This is the non-regularized version I showed you. This is Info-SID plus Kalman plus MPC. And here's the control actuation. Those are all very similar. So, okay, it doesn't seem to matter whether I used the data-driven method, which data-driven method I used, or I just went for the standard control system and identification toolboxes in there. So what can possibly go wrong here? So and this is one of the reasons why you don't want to be doing some of this for aircraft is turbulence in aircraft, disturbances, as you mentioned. So here is typical disturbance over actually twice the horizon, and a disturbance is in vertical gust velocity. And this corresponds to, I think 40,000 feet altitude and the boundary between medium to severe turbulence. And it's given by a third order filter, called the Dryden-Gus model. And when you try and sell your plane, you have to show how your system will respond to certain levels of turbulence, or the FAA, at the moment at least, won't let you fly unless you do that. And so you have to be able to put that into your simulation, see what happens. Now, better speed up again. If you didn't control it, this is what would happen. So here we're seeing horizontal velocities changing by 60 feet per second, climb rate also getting up to 60, 70 feet per second, there's big oscillations. This is basically, you'd pay a lot to have a roller coaster do that. You'd better be hanging on. This is definitely grip the side of your seat stuff at this point. But it is easily controlled, and every plane we fly in has simple controllers, actually gain schedule PI controllers often that suppress this. It's not a difficult problem, but it's kind of like a benchmark problem, okay? But it has to be controlled, the plane, and it's typically not too difficult to control. So these control methods also work for it. What do we normally do for our control methods is we employ Kalman filtering. One thing that you notice here is that the data-driven methods don't see, none of the methods there give you what happens when a disturbance comes in. They're talking about input-output data. This is what you had in your simulation. This is maybe what you had in your experiment. You didn't see the disturbance in there. But you've got unmeasured disturbances and measurement noise on the outside. So a Kalman filter gives the optimum trade-off for state correction under those circumstances, depending on the variance or invariance of those disturbances. And how do we fix that problem? Because our data-driven controller doesn't do that at all. So we don't see the disturbances, and actually, I'll show you, we don't control them either. So one way of fixing this is to try and write down an evolution equation for this conceptual G here. Because when you think about how you form these UP and UY, you look back over a horizon, which was 30 time steps in there. And then the next time you kind of solve the problem, you lose one data point, and you get one new one. But 28 of them are exactly the same as you had before. So how different can the solution be in this? And of course, it can't be very different. So you can try and figure out what's the evolution equation to go from the solution at one time point to the solution at the next time point. So let's do that. I'll run through the details. Well, here you have to read papers to get the details. But essentially what I found here is you can write it down as a state space representation. It's now slightly approximate. You need to lose rank 1 in your Hankel matrix, and maybe it's an approximate, and it's basically fitting quite a lot of noise, but you can evolve this xu, xy variable like this, u, and you can actually use it to make a prediction of what your next measurement is going to be. So now that you have that, and it's a state space, you can predict the next measurement. Why don't I just call Kalman, one-line command in MATLAB, and then I can get a Kalman filter that tries to put in the optimal correction to that state. Okay, you can do that. And now you split it up. I've got a system where the inputs are no, outputs I'm measuring with some noise, and now there's some disturbance that I don't measure. And we assume in classical Kalman theory that it's zero mean and a particular variance. And so now I've got dynamics here for this uy variable, which have the known piece, but some unknown piece. And so I use the known piece to update a model estimate, and I use the measurement minus the prediction to correct for the estimate. So it's standard, completely standard Kalman filter. There's a variety of ways of doing that. Here I've done a current estimator, if you're familiar with Kalman theory, that does an immediate update to the time step. I've written down the estimator equations, but this is really nothing you couldn't get out of a standard textbook. And you can calculate what the estimation error dynamics are. You see the usual A minus KC or LC, depending on your notation. And then there's a disturbance input and then a noise effect. And the optimal Kalman filter trades that off. So that's really standard. Here's a method, but that's just the LMI method. One or two of you might be interested, but it's exactly what you know. And here's the results. So now we're doing two things at once. What we're doing is we have the gust and the step response. And this is data-driven control. The shading is plus or minus 1 standard deviation on that. This is completely standard toolbox N4 SID, Kalman MPC. This is the one I just showed you, making a Kalman filter out of that signal matrix model. These methods, the data-driven methods, don't see the disturbance and they don't attempt to correct it. And they do really badly as a result of that. And actually, if you look at those Monte Carlo statistics again, here's the mean square error. Here's standard classical ID toolbox Kalman filter. And here's the one I just showed you with a higher state dimension. They both do pretty well. And these ones do very, very badly in here. And if you look at the control energy on this last plot, you can see the control energy for standard data-driven control is not very big because it's not even attempting to reject the disturbance. It's not seeing the disturbance in there. Whereas a lot more control energy is needed for both of these methods because they see the disturbance and they correct it in that. So observation here is that these regularized data-driven methods do a poor job of detecting controlling process disturbance. I shouldn't say they do a poor job, they do no job at all. They just miss it. And so you're not rejecting those disturbances. Standard Kalman filtering will detect and control disturbances. And I think I actually showed you that one, so we'll go over some closing comments here. So here's this decomposition. It's just a very simple variation of just taking the null space out of the Willems lemma and doing a lower triangular decomposition in there. You get automatically a causal decomposition of the past and future. You get the minimum variance unbiased prediction of the future output. That's if your data in here is noise-free. Only your implementation data is noisy, which is the case you get for a digital twin. And obviously, as before, model data and past measurement data determine the model quality. So Kalman filtering, I've just shown you a way of implementing Kalman filters in this data-driven framework, and I hope I've convinced you it's essential to do so for almost every problem we face because you always have disturbances in the system. And it integrates very easily into a predictive control structure. It doesn't integrate easily into these hierarchical structures where the real physical state has some meaning. There's a state here. It's not a minimal realization in there. It's a larger state, but we are still doing classical state space design methods with it. So if you're in one of these systems, then aircraft don't fall in this category where you want to do cheap and easy, just crank the handle, quick design and get some benefits. After all, you can't crash a building, so I'm not too worried about letting this loose on a building control problem. I'm not flying in a plane where this has been done. Then go ahead with this. So here are some of the potential benefits. So for data-driven methods, you do or you can simplify a time-consuming modeling process, and this will work well for simple systems where you don't really need to be using a time-consuming modeling process. But if it's high-value, safety-critical, mass-produced, hierarchical, distributed, then you do need to spend the time doing a good job there. It's fast to implement. So, I mean, I showed you everything that ran there. So for each one of these controllers, there's 30 Monte Carlo runs. There's a design done for each of the 30. And then there's the simulation itself. I pick one of those controllers, the whole lot runs, including all the simulations, in probably 30 seconds. So it's essentially nothing in computation time. So even though my state dimension in this case was 120, and that for my big state, 120 on a laptop, even an old laptop, is not a huge state dimension to use. So there's no computational ones. The drawbacks, though, data is messy, unreliable stuff in there. The information you want is there, but it's probably buried very deeply. All of the experimental and identification considerations we look at in system identification, they just get subsumed into the quality of this, and they appear in the covariance of the output errors. Operational data is poorly suited to actually characterizing system behavior. And when I say operational, I mean there's a controller already in operation on that system. And the job of a good controller is to hide variations in the plant from you. That's what sensitivity means, variations in the plant response compared to variations in the open loop. So if sensitivity is low, then you're not getting any information in your data. And you'll find that you can't really do a nice job with this. It's difficult to incorporate physical knowledge, and this is important in MPC in some applications where some of the physics tell you immediately that certain behaviors are not possible, but that your model's not guaranteed to generate them, and you end up with feasibility problems. And I pointed out it fits very poorly into a complex physical hierarchical system in there, which large-scale or cyber-physical systems typically are. So I'm looking for nice applications. I think the building control is a nice application of this. If you've got any more, if you've got any more, let me know. But that's another potential one I think might come up is within certain grid operations and power systems where you've got multiple consumers and they want to connect things to the grid and they're not prepared to tell you exactly what they're connecting, but you want to check whether they meet your specifications for maintaining margins on the grid. The only thing you get to see is the signals they have at the connection point. And there you might be able to characterize something in these terms. I think there's potential there. And I'm still looking at the one where you've got big PDE models, particular aero elasticity models, and then you're trying to get at least a manageable representation to use in control design. There might be some possibility there as well. I think that's it. Now, I'm sure there's more, and so I'm happy to receive suggestions or receive any questions. So thank you very much for your attention. I'll stop here. Thank you.
Questions?
Yes. Oh, okay.
So when you, at the end, you talked about, you go to the next time step.
Yep.
Throw away most, you basically shift your horizon.
Exactly.
Using for the data for each.
Yep.
Right?
Yep.
Do you really need to do that, or can you why not just hold on to all the data and just collect more data.
Essentially,
Because these just get bigger and bigger.
bigger and bigger. But actually, they don't, it's just an efficiency type of question. They don't have to get bigger. The thing is, then you end up with essentially a growing horizon. And so computationally, you start struggling at some point.
Yeah, I was
Yeah.
hoping that there was some kind of trick where you could recursively update it, you know.
Well, actually, this is what that trick I showed you does.
Yeah, but you're throwing away data. Okay.
You don't need it, because actually you only need to go n+1 time steps in the past to be able to uniquely determine your initial conditions.
Oh.
So that's a, yeah, Chris.
Thank you, Roy, for a very nice talk. Building upon that, it feels to me as
Yeah.
though, I'd like to go on more than just feelings, but
Yeah, okay, no.
it feels to me as though preservation of all of the old data, in addition to making computations burdensome, could be problematic if there's some time variation in your system.
Yeah.
And that's why we often want to apply a discount factor when we're doing, for example, RLS identification. And I've been thinking about that in the context of this, because it seems like, as you said, the only thing that you need to uniquely determine that initial condition is you need the rank of that data matrix to be what is it, N, right?
Or full row rank.
Full row rank.
For you, yeah.
Yeah, it seems as though if you have a system that is time varying or has some nasty nonlinearities,
Yeah.
even though you're not actually modeling the nonlinearities, a differential equation does exist for that system, that something would break down, but yet I don't.
Oh, you
see
do.
that in the-
Well, but no, actually, no, of course, something will break down and say, but these representations are exactly equivalent to linear time invariant state space.
Right.
So there's no nonlinearity and there's a finite state, and finite state's a pretty strong assumption.
Yeah,
Oh,
right.
you know from controllability and observability, you only have to go n+1 observation points and you can completely reconstruct the state exactly.
Yeah.
Now, in many systems, that's an approximation, but it's exactly the same result here.
Yeah, so I would think a real challenge with preserving all kinds of old data is if you have a nonlinear system and
Yeah.
your operating regimes are changing a
Right.
lot, then you're not discounting the
Yeah.
time you have.
But actually, you can consider scheduling your H matrices. I mean, you could be running different of these experiments and just for aero problems where you can schedule against dynamic pressure, for example, and you could be looking, you've collected a whole series of data and now your job is to blend, to go from one regime to the other. But you could use that in that framework. So thanks.
Please.
Just a quick question. So
Yeah.
Are you aware of any work which is trying to extend these to actually nonlinear systems where instead of, eigenspaces, there's manifolds and so on?
Actually, yeah, there are people attempting it. So one of them is Mathieu Lazare in Delft. Sorry, not Delft, Eindhoven. He is doing that because sometimes you can actually, for things like parameter varying matrices, you can create your H matrix out of H plus a function of a parameter times other matrices. So in very structured cases, you can still use the same thing. But fundamentally, what we're doing here is we're applying a linear control and a linearized model to a nonlinear system. But actually, that's what we all do in every single case of control anyway. And so you can prove things which are proven here about the theoretical considerations. Of course, they all somewhat break down at different points. So you have to really test and see how much that linearization thing is. But there are some attempts to sort of translate nonlinear models into very similar models. I mean, I mentioned just simple scheduling, but if you have a linear parameter variation across a range, then you can imagine doing a linear variation of some of Hankel matrices, and then you could carry this through. Yeah. Actually, I've got one comment to make. I should point out something. If you go to the papers and read papers which compare data-driven and regular control, they don't do any comparison on the disturbance one, but that's fine. But when you go and look at the papers, they typically show that the standard N4 set in Kalman performs worse. And when I first did this, it did perform worse in there. And the plot in the paper shows it performing worse in there. And so I thought, why should it perform worse? It's doing a Kalman filtering, it's all of these nice things. What can possibly go wrong? What's possibly wrong is the default setting for N4SID in the MATLAB toolbox has I would call it a bug, essentially. If you don't provide it with a horizon to estimate the initial condition over, it seemed to choose a horizon of 1, even though it was trying to estimate a 7-state model in this. And it gave terrible results. The fit was less than 1%. Once you provide it with a horizon, which is about the length of the prediction horizon you'd like to do, the fit goes up to 99.5% in this, and it performs spectacularly well. So all the comparison stuff I'd seen so far had just used the default settings, which is totally reasonable if you want some, I just want to crank the handle, do the same thing and just calculate, do N4SID. You can do it in a couple of lines of MATLAB, N4SID, Kalman, and then just stick it in the implementation in this. So, or N4SID, Kalman state feedback, and you're pretty much done. But if you don't set that parameter for the estimation buffer size correctly, the N4SID doesn't do very well. So fixing the bug changes the perspective a little bit. But anyway, so even if you go and look at my papers, they show the bug, and I can't explain why N4SID was so much worse. It's not.
Let's move past time, so let's thank our speaker again and then people can come back to talk.
Thanks very much. Thank you. Yeah.
About that question I asked.
Yeah. About the disturbance?
No, at the end, about throwing away the data.
Yeah.
Is that still true even if Y is noisy?
Yes.
Because you don't, because I
Oh,
would
okay.
think, I would think that in that case, you don't hold on to as much data as you could in order so that when you do that, you already know all the noise kind of washes out.
Okay, you got to consider what the 2 points where there might be noisy data. So you have a input output sequence you use for language.
Yeah.
And you also have measurements of why you use the condition.
Yeah.
Okay, and so I thought you were referring to the initial condition, the length of that.
Well, as I understood it, with what you were doing is when you're building up your H matrix.
Yeah.
Just past U and Y.
It's not the immediate one, it comes from maybe an experiment or a digital twin, but it is, it's not, I could say.
That was my misunderstanding.
Okay.
I was thinking what you were saying is you look into the recent past.
Yeah.
And you use the control and outputs from the recent past while you're controlling it to re-identify your model.
No. Essentially, I guess I apologize, it wasn't that clear, but yeah, no, the model. H matrix-
No, I got everything up until that. When you started talking about recursions and things like that.
Yeah.
on-
No, my H wasn't changing at all.
Okay, okay.
It was just that,
Okay, no, I get it now.
Yeah.
I actually get it. That was what I didn't understand. So, but you could do that, right? You could re-identify
Yeah.
H.
yeah, but then what happens is you run into an excitation.
Well, that was gonna be on the next slide. So that's what happens is when you just kind of evolve into a situation where you don't have persistence in your
Yeah,
excitation.
that's right.
And
Then your decomposition doesn't work anymore either.
yeah,
You can't take the
Right.
U and get a lower triangular
Yeah.
version of it.
I see.
Yeah, so.
Fascinating talk. I'm gonna have to try this in my wave energy problems.
Okay, yeah, no, sure, it's kind of
Because it's a good situation because in order to get the hydrodynamics right, you need a lot of modeling, and the modeling is different for every single site.
okay, yeah.
And so it's exactly what you're describing.
Right.
The investment that a company would need to put into coming up with a model for a 10 buoy array
Yeah,
is so exorbitant that they're just not gonna do it.
yeah,
But if there was like a standardized way to do this, is that sort of often.
just crank the handle
Yeah,
on the
yeah,
drive.
just crank it.
Yeah, no, I know that, that's a nice example. I have,
Yeah.
yeah.
Yeah,
I'm looking for those.
I'll let you
yeah.
know how it goes.
I'm just.
Years ago, Jeff, how are you?
Good to see you. Great. Great sound.
So you were retired. Oh. I retired 6 weeks ago. Yes. And that's why I give you the freedom to listen. Around.
Yeah, Tim told me your wife's in Europe.
She's in Europe this week, so she's in Europe. And they decided now to attract distribution US researchers. That's, there's nothing targeting going on. But she's gone sabbatical in Berkeley, and so I'm unofficially there. 6 months. Basically.
Excellent. That's a good place to hang out.
Yeah, it's good.
Less snow.
Yeah. A little more snow.
Well, you would be.
Yeah, I am. It's not right. Let's see.
Well, good seeing you.
You too.
Very nice.
Thank you very
Take
much.
care.
Okay, you too.
One thing New York State is beyond now.
Hey, Roy, thanks for joining.
Yeah.
Quick question.
Yep.
So you said buildings are 50% of CO2 emission.
40%.
40%. Yeah, okay, 40. But where did you get that data? Because it doesn't match the data from Bill Gates, that from the book I showed you.
Okay, that's interesting. I
It
got
does
that
not,
data
because
from-
he says buildings are only 10%. So, but that doesn't count the electricity used in buildings, because he counts electricity generation as a separate category.
Okay, now this is counting
And
that
that-
for sure.
Yeah, but electricity generation is about
Yeah, so-
25 and 28% of greenhouse gases from electricity generation. But of course, not all electricity goes into buildings. right?
But actually, it's also counting the use of building and industrial and commercial buildings.
Industrial to, okay, because, okay, so that's good, because, okay, now that's starting to make sense, because
But this is.
there's,
report.
okay,
Gives this
it depends on
breakdown.
how you do the accounting.
Yeah, how you do the accounting is true.
Because he says buildings, but he counts industry separately.
Okay.
So,
I
He says
think-
making things, so making things is like
And a
15%.
I'd have to look and see what the other categories.
Yeah,
Yeah.
so he's got a different way of counting.
Yeah, but there's a kind of a European Commission report.
Yeah,
that has
okay, so
gone
I
through-
can see now that if you add the industrial buildings.
Yeah, potentially, yeah.
And then, because the industry, what's really, there's two things that exceed everything else. It's making cement
Actually, that's
and making
counted.
steel.
Making cement is counted
Okay. so
as
they-
embedded energy in a building.
It's, okay.
Yeah,
okay,
so
Okay, that's why you
that's why
get
it's
to
so
40.
high,
Okay,
yeah.
makes sense.
And obviously you're not controlling that.
No,
That depends
well,
on
the
the-
problem is because when you make one molecule of cement, I mean, you produce one of CO2.
Yeah.
So then, and then it takes tons of energy that they have to burn fossil fuel for that.
They
They
do.
cannot use electricity.
Yeah,
We figured it out.
Okay.
yeah. It's where you draw the boundaries on your count.
Counts industrial buildings too, which counts for
So Roy's stuff is.
Okay,
No, it's.
Oh, there, okay. My stuff is, my stuff.
All right. Tomorrow.
Huh?
Are you coming with us?
Yeah, because on says 20 minutes, but that'll be half an hour and,
Yeah, sure, sure.
Over by the array side,
Yeah.
that little small. I'll do that. Just ready. Comes, I'll walk out.
Well, no, it's a push for a lot of people to say, I'd like to do it without having to know the physics. And so they want a simpler method. So that's what I mean by including the physicists people.
I see. Sorry.
Yeah, no, that's it.
Is there some way to say, okay, so I guess the context is I'm trying to work on. I'm on.
The years that you always have to
Uh, with,
and they always let
Yep.
us to later.
And the issue that it's, you know, they're trying to try a bunch of different kind of chemistries and designs.
Yes.
You want kind of rapid, development of these models or
Yeah.
lack thereof.
Yeah.
But I guess, and
It's good.
so there are
It
teams
seemed to be good.
doing high fidelity models, PDs and
Right,
PDs, tricky. So I felt like this might be appropriate, and when I got to talk to, Dr. Colson.
Yeah.
Top those thoughts.
Yeah.
But then the thought is, even then, it feels like a waste to completely ignore any physics. So then,
Yeah.
do you have any ideas on how you would try to implement that back in?
Yeah, no, this can be tricky because you don't end up with sort of a data-driven model. But if you look at regular state space, it's often there's a part of the state where you know that. So, for example, you know that position is the integral velocity. You can choose position and velocity in particular states, and then use identification methods for the rest. You know, the things that you find difficult to model, like friction parameters,
Yeah.
what are response times of tricky, complex things, sort of your electronic circuitry, which has all sorts of parasitics involved. And so then they say, okay, I really should try and get a model of that experimentally, but the pieces that I do know, I should try and include those. And then you end up with a blended sort of model.
Okay, so some parts of it are kind of like sequential, also sure.
Yeah, and so, but most system ID people say, oh, that's just system ID, and they're right, it is. You take the pieces that you know and then try and fill in from that other pieces you don't. Or you might even know certain ranges of parameters. So when you're doing your estimation of these parameters, you try and bound line with ranges that you from physics know are reasonable. So for some things like you know parameters are positive in some just from physics. But if you do it using noisy data and do an estimation, they might not always be positive. And so something this is not really describing the situation. So there you end up modifying, and there it is involved. You know, it takes you have to put the physics in, you have to figure out how to get as much of the physics as you know into the data and the identification steps, and it gets very involved. And so because it's so involved, this is when the temptation people say, "This forget the physics, just go purely on that." And then
Yeah.
dangerous.
So I guess you kind of mentioned like I guess on a high level, like how would you imagine kind of blending the two methods?
Well, I mean, you mean just now?
Yeah.
Well, actually, often there are some pieces of systems where you do get some measurements, the internal stuff, or you know that say you've got velocity and positions in there, so you can put those as states, and maybe you can measure those ones, and then you have other things in your system. So battery is kind of a difficult one. I don't know what internal variables you might actually get to measure. But you have a bunch of internal variables, and some of them you might be able to very closely relate to states you know are the case. So in an automotive one, and obviously you can't get a good model between throttle response and engine torque. There's a very complicated model there. But from engine torque to velocity and position travel, you've got a very good model for that part.
Yeah.
So you get that part, and then you try and get a model.
Yeah.
And then in that case, that's just joining the models together. But sometimes it may be much more complicated in the interconnection. So
I see.
this is really what makes it tough, and you really have to work at it. So yeah, in those cases, if it's a model worthwhile, it's something you're mass producing, and you really want to understand the characteristics, then you have to invest the effort in figuring that out. So how to do that?
Yeah. I guess, sorry, if I can ask one
Yeah,
more question.
yeah.
Would it be reasonable, if possible, because I know it isn't necessarily always possible, to embed some of the physical knowledge into the constraints between your input and output?
Sometimes, but between the input and output, it's going to be a dynamic constraint. So it's not just going to satisfy a simple condition. It's going to satisfy a recursive condition or a very large scale condition. And that sounded kind of hard. That's essentially, that's the dynamics you're trying to model. So, that can be difficult to do that way. It's usually not possible to do it like that. So you have to, if you have probing signals or other signals that give you more direct information about just a piece of the problem, then you can identify that piece correctly and then try and reproduce the rest that you don't know. So that's what makes it a bit of a challenge in that situation.
Yeah, thank you so much.
Okay, no problem. Thank you. All right.
Yeah, the biggest turnout we've had since